Students, please quickly call all of your friends. Just taking quick attendance. So today we're going to start with chapter number 2, right? What is involved in creating a data science or a machine learning project? What are the steps that are involved in creating a data science or a machine learning project? That is what we're going to be looking at today. Okay. I want all of you to pay attention here. I know that some of you found the quiz difficult. I've evaluated some of your answers. It is a thinking mindset, guys. You have to evolve the right mindset to be able to solve this type of question. So it is very important that you understand how we take up a data science case study and how we solve those problems. So that is what we are going to look at today. There are some fundamental skill sets that you will have to learn through this. We will be going through that in detail. Just hold on, guys. So first thing we're going to do is install Jupyter Notebook. Okay. I'm going to give you the instructions for this. So all of you have Windows, right? எல்லாருமே Windows தானேமா? Students? Yes, no? நம்ம கொஞ்சம் பதில் சொல்லுங்க students. Do you all have Windows?
Yes, sir.
Okay. So first step before we begin the class, I want everyone to click on the link that I've sent in the chat to install Jupyter Notebook. Come on. Please click on the link that has been sent in the chat to install Jupyter Notebook on Windows. It will give you detailed instructions on how it can be done. Come on, quickly start. We'll also share another Medium link to help with the same. Windows 10 is specific. You can choose the Medium link also. If you don't have Python, guys, hope all of you have Python on your system. எல்லாருக்கும் இருக்கா Python? Come on, guys, say yes, no, no, not sure. Yes, only Dileepan and Janani are in the class. What about the rest of you? It's only 4 or 5 students are answering every class. Vijay Paul Raj, உங்கள்ட்ட Python இருக்கா இல்லையா சிஸ்டம்ல? How do you check if you have Python or not? Can anyone tell me? எப்படி check பண்ணுவீங்க?
Python version, sir.
Python, can you see my screen? Python, if you give the command and you press enter, if you're able to see a command prompt like this, that means you have Python. And the version that you have will be mentioned here. Okay. I repeat, all you have to do is click on Python or type Python on the screen. So type So type Python on the screen to see if you have Python, right? You will have the version which is mentioned here. Can all of you do that right away and tell me if you have Python on your systems? For those of you who have just joined the call, what we are trying to do here is we're trying to get Jupyter Notebook set up. on your independent systems. Guys, it's not going to take the entire day. I want you to work quickly on this. Quickly download Jupyter Notebook, install and set it up. Come on. So I'll share the median link on the screen for those of you who haven't seen it. So this will be the link, installing Python in Jupyter Notebook to Windows 10, right? 64-bit, hopefully all of you have. So downloading and setting up Python, that I think you can skip because all of you have Python on your system, right? So then you can move on from here. So install virtual env, then you upgrade the pip, right? You activate the bat file, you install NumPy, then OpenCV, Matplotlib, then finally Jupyter. Come on, I'll give you time. 10 minutes time. Come on, quick. Students, are you following? Are you doing this? Can you please give me a yes in the chat? If you're doing it, please give me a yes. Want to see your chat. Only Vijay Paul Raj is doing, is it? What about the others? Come on. Please go ahead. Start installing Jupyter. Inapa, Veru, Vijay Paul Raj, Dilip and Tatu, nobody is responding. Are you guys doing? Those of you who've come in recently, those of you who've just come in, please click on this medium link. You have Python already installed. So Python install aayirukadnala, start from this part of the page. Right? Start from this part of the page, which is from step number 7. So start from step number 7, since you already have Python installed, and start installing Jupyter Notebook through a series of commands. Are we done, guys? It's been 10 minutes. Have you completed installing Jupyter Notebook? Can you please tell me what stage you're on, students? In the stage, Diliban, can you unmute and tell me what stage you're on?
Sir, installing Jupyter.
எந்த பார்ட்ல இருக்கீங்க? பைத்தன் பிப் இன்ஸ்டால் மத்ததெல்லாம் முடிச்சிட்டீங்களா? ஜூபிட்டர் பண்ணிட்டீங்க?
Yes, sir. Yes, sir.
ஜூபிட்டர் மட்டும் தான் பண்றீங்க. Yeah.
Yes, sir.
Okay. What about Devadarshini? Devadarshini?
Sir, installed, sir.
Installed. Very good. Very good. What about Adi Sivaprakasam?
Finished, sir. Installed, sir.
Finished. Very good. Hidayat Nisha. Hidayat Nisha.
Installing, sir.
எது இன்ஸ்டால் பண்ணிட்டு இருக்கீங்க?
Jupyter.
ஜூபிட்டர் லாஸ்ட் ஸ்டெப் வந்துட்டீங்களா? கார்த்திக், Karthik, can you please unmute and answer, Pa? Have you installed? Karishini? Karishini பண்ணிட்டீங்களாமா? Students, I'll ask you to share results, so please ensure it's installed properly. Karishini, have you done it? Karishini, please unmute, ma.
Installing, sir.
Installing. எந்த பார்ட்ல இருக்கீங்க?
So starting as a network issue, நால slow-ஆ தான் sir இருக்கு.
சரி. Okay. Okay. So students, I'm going to share screen. So before we go ahead with installation, so let's start off the lesson for today, right? So we have to go through quite a bit. So just bear with me for 1 second before I share screen. Okay. So today we're going to look at how you're going to do a machine learning project, right? So your lesson talks about working with real data. So when you're learning about machine learning, it's best to actually experiment with real world data and not just artificial data sets. So fortunately, there are thousands of open data sets to choose from across different domains. So some of the places that you can look at are popular data repositories, right? Examples are Irvine Machine Learning Repository, Kaggle data sets, right? That's one place where you can look at, or Amazon AWS's data set. So these are some of the popular data set repositories that you can look at. Meta portals are basically, they list, meta means one level above. So meta portals list other open data repositories, dataportals.org, opendataMonitor.eu, quantl.com. So other pages where you can see open data repositories are Wikipedia's list of machine learning databases, Quora.com, and data sets in subreddit. Okay, so these are some of the repositories where you can actually get lots of data, right? Okay, so moving on. In the topic that which is given to us, we are going to see through these 8 steps. Look at the big picture, get the data, discover and visualize the data to gain insights, prepare the data for machine learning algorithms, selecting a model to train the data, fine-tuning the model, and presenting the solution, launch, monitor, and maintain your system. So these are the steps we're going to go through today. Okay. So in this topic, what we're going to do is we choose the California housing prices data set, use it from the StatLib repository. So the data set is based on data from the 1990 California census. So it's not exactly recent, right? But it has many qualities that are useful for machine learning. So we're going to pretend it's recent data. So when we look at the big picture, first thing is, imagine you're working at Machine Learning Housing Corporation. So your task is to build a model of housing prices in California using the census data. So data has metrics like population, median income, median housing price for each block group in California. So block groups are the smallest geographical units. For this, the US Census Bureau publishes sample data, right? So we call them like districts, just like we have districts, they call blocks. So your model should learn from the data and predict the median house price in any district once it is given all the other parameters. So what are the other parameters? So ரொம்ப simple. நம்மளோட இந்த particular case வந்து it is a direct case of linear regression. So you're given an equation y equal to mx plus c. right? Y equals mx plus c. Now, what is it that you are given? You are given the value for x, right? You have to find out the value of y. So how do you do that? You do that through curve fitting, right? So you have n number of instances. Say you have you train the data set for n number of instances to find the right values of m and c, such that if you plug in the right value of input, you will get the correct value of output, right? So that's what we are doing. Very crudely speaking, that's what we're going to do. So here, what are the different inputs? You have the population, you have the median income, right? And so on and so forth. And you have to predict the median housing prices. Okay. Is that clear, everyone? So that is the objective, right? So you are a well-organized data scientist. So the first thing you do is you pull out your machine learning project checklist, right? Let's see how we can evolve the steps that are part of machine learning. First thing, the first question you ask your boss is, what exactly is the business objective? Why are we doing this? Building a model is probably not the end goal, right? So what does the company expect to use and benefit from the model? So what is the purpose of the model in the context of the business? Why is this needed? This is important because it determines how you frame the problem. What are the algorithms you will select to solve the problem? What performance measure you will use to evaluate the model, and how much effort you should spend tweaking the performance of the model. So your boss's answer is that the model's output, which is the prediction of the district's median housing price, will be fed to another machine learning system, right, along with many other signals. So the downstream system will determine whether it is worth investing in a given area or not. So getting this right is critical because it affects the revenue of the organization. So let's look at this diagram, which is given here. You see this diagram. This talks about the entire structure of your components. So you have certain upstream components. Upstream na idhukku munnadi vera systems, downstreams are systems that come after it. So upstreams are the systems that feed your system data. Downstream systems are the systems to which you feed your output as input data, right? So as far as your component is concerned, this is downstream, right? And this is upstream. Please remember this terminology, upstream, downstream. It's a very commonly used lingo in corporations. Whenever there are multiple systems that are in a pipeline such that input of one is the output of the other, they're connected with each other, very common to say upstream systems and downstream systems. So please remember that. And this is where your model comes in. So what does your model do? It predicts the median house price for a given district, given the other parameters like population, median income, so on and so forth. And that is stored in a database. And it is then used along with other signals to a downstream system that is used to predict whether it is worth investing in this place or not. Right? How many of you understand up to this point? Quick responses in the chat. How many of you understand? Quick responses, guys. Come on. I want to see quick responses from people. How many of you understand up until this point? I want to see some yeses. Come on, guys. The Ribbon says clear. What about the others? Vaishnavi Devi, Vijay. What about Kirtana? Kirtana, Jose, Janani, Sharmila, Shubhashweta, Sujit, Varshini, Vartiha Harshini. Do you understand? Come on, students. I want some responses from you. Okay. Moving on. Okay. Now that we saw the system, right? So this is how a system is looking like. It's called a machine learning pipeline. Okay. So what do we do here? We start off with understanding what a pipeline is. So pipeline is nothing but a sequence of data processing components, right? Very common in machine learning. So there's a lot of data to manipulate and many data transformations to apply. So components typically run asynchronously. That is, they run independently. Each component pulls in a large amount of data, processes it, and spits out the result in another data store. That is basically what you see here as a database. Data store is a general term used for a database. So there's a processing which happens here, and it gives out the data to be stored in this database, right? So then sometime later, the next component downstream in the pipeline pulls the data from the data store and spits out its own output, right? So that's what is happening here. For example, your district pricing's data comes from the district data, which in turn is actually put in by the upstream components. Likewise, your output goes into the district prices database, which in turn is used by the downstream component investment analysis for further information. Okay, so that's exactly what a pipeline is. So each component is fairly self-contained, and the interface between components is simply the data store. So what makes the system quite simple to grasp, and different teams can focus on different components. That's why we have a pipeline. So we have clear separation of concerns. If a component breaks down, the downstream components can continue to run normally by just using the last output from the broken component. So this makes the architecture robust. So for example, if we take that there is a particular breakdown here, right? If this component breaks down, right? If this breaks down, so downstream components can take data here, right, from the database, and they need not be immediately affected, right? They're not immediately affected because there is no direct connection. If you notice, there is no direct connection. They're connected through the data store, so they're not immediately affected, right? So let's move on. So this is one of the major advantages of having a pipeline. Now, this makes the architecture robust, and if there is a component failure, the downstream components can continue to run normally by using the last output from the broken component. On the other hand, a broken component can go unnoticed for quite a long time if proper monitoring is not implemented. So the data gets stale and the overall system performance drops. Let's see what does this mean. So for example, say in this particular system, we find out that this component, your district pricing engine, is broken, right? Of course, for some time, it's going to take in values. The investment analysis engine will take in values from the district prices database. But over time, what will happen? Your district pricing will start predicting wrong median prices, correct? When the system is broken, it will start predicting wrong median prices. Now, the wrong median prices will get stored in the district prices. Obviously, if the decision for the investment is going to be based on wrong predictions, the overall quality or the overall performance of the system comes down. So you need to have a monitor, right? You need to monitor the overall performance of the system from time to time in order to understand if everything is going all right and if the system components are producing the right data. You understand what I'm saying, students? Yes? Yes or no, guys? Do you understand? Okay. Moving on. So the next question that you want to ask is what the current solution looks like. It will often give you a reference performance as well as insights on how to solve the problem. So your boss tells you that, hey, now what happens is district house prices are estimated manually by experts. So the team gathers up-to-date information about a district, excluding the median housing prices. They use complex rules to estimate the median housing price. It's very costly, time-consuming, and the estimates are also not great. The typical error rate is about 15%, right? So with all the information, you're now ready to start designing your system. So the first thing you need to do is to frame the problem. Remember, always the first question that you need to answer is, what is this problem? Is it a supervised learning question? Is it an unsupervised or a reinforcement learning? Is it a classification task? Is it a regression task? Or is it something else? So should you use batch learning or online learning? So before you read on, just pause and answer the question. Come on, guys. So first question, is this a supervised, unsupervised or reinforcement learning task? Come on. Who can quickly answer? Is this a supervised, unsupervised, or reinforcement learning task? Vaishnavi Devi, is this a supervised, unsupervised, or reinforcement learning task? Vaishnavi Devi, can you unmute and answer, ma? Is this a supervised, unsupervised, or reinforcement learning task?
Sir, it's supervised, sir.
Why?
Sir, we are giving the data and also the labels corresponding to this.
Very good. Very good. That's right. It's supervised. Good. Right. Next thing. Dileepan, can you tell me, is it a classification task, a regression task, or something else? Is it a classification task or a regression task or something else?
The regression.
Very good. Why?
So we don't have a different types, so we just gonna find the values on
very good. Excellent, Dileepan. That's right. It's a regression task because we're not classifying anything. You have to predict a numeric value, right? So that is regression. Very good. Harish, can you tell me whether you should use batch learning or online learning?
So batch learning, sir.
Why so?
So based on the past historical data, we'll be predicting, training the model once, and we won't train for new incoming data. We'll be just predicting for that.
What is the reason for that? What you said is right. That is what batch learning is. Why do you not need to try with new data?
So prices won't be coming frequently. Change.
Very good. Price changes are not that
every day or every month, sir.
Very good. Very good. That's
Yes,
right
sir.
answer. So price changes are not very frequent. It's not a very sensitive or a volatile industry. So you can afford to go with batch learning. Excellent students. Good job. So what is the answer? Let's check. It's a typical supervised learning task. You're given labeled training examples, right? It's a regression task. You're asked to predict a value. It's a multivariate regression problem. What does multivariate mean? There are multiple variables in the problem, since the system will use multiple features to make the prediction: district population, median income, etc., etc. So in the first topic, you predicted life satisfaction based on one feature. Remember, guys, life satisfaction is predicted based on GDP per capita. So it was a univariate regression problem because it had only one variable, and there is no continuous flow of data in the system. So there is no need to change data rapidly or adjust to changing data. Therefore, we use plain batch learning. Okay. So if the data was huge, you can either split the batch learning work across multiple servers using something called the map reduce technique, which we'll see later, or you can use online learning techniques. But here, that's not a problem, so we're not going to bother with that. Now, selecting a performance measure. The next step is to select the performance measure. Typical performance measure for regression problems is the root mean square error. It measures the standard deviation of the errors in the system, right? For example, RMSE equals 50,000 means 68% of the system's predictions fall within 50,000 of the actual value, and about 95% of the predictions fall within 100,000 of the actual value. Okay. Now, before that, how many of you guys remember statistics in terms of how data is distributed in a normal distribution? Can anyone tell me how many of you remember how data is distributed in a normal distribution? Come on. Anyone? Anyone remembers the famous bell curve? Yeah. Can you tell me what are the labels for this curve? Can anyone give me the labels? What is the center? Come on, guys. What is the center? What is this? Can anyone tell me what is the value of this? Statistics marketing law. What is the value of the center of the bell curve? Harish, can you tell me? Center of the bell curve.
Median. Median.
Think median.
0 SD, 1 SD. Standard.
Mean is the center. Right?
So mean is the center, and
what is
1
this?
SD.
Very good. 1 standard deviation, and this is 2 standard deviation. Likewise, this side it's also mu minus 1 standard deviation and mu minus 2 standard deviations. Okay. Everyone are able to understand? So this is the standard bell curve, right? It is centered around the mean, right? And we have 1 standard deviation and 2 standard deviations on either side. Okay, apologies for the pen. So this is mu plus 1 standard deviation, and this is mu plus 2 standard deviations on the right hand side of the curve, where it is mu minus 1 standard deviation and mu minus 2 standard deviations on the left hand side of the curve. Everyone knows what standard deviation is? Darshini, can you tell me what standard deviation is? Darshini, what is standard deviation? Come on now. Devadarshini. What is standard deviation? Does anyone remember? I'm not asking for a definition. How do you calculate standard deviation? Come on, students. These are some of the basic things. You should not forget this. How do you calculate standard deviation?
Square root of variance, sir.
Square root of variance. Okay. Okay. But how do you calculate it? Supposing I give you the numbers 1, 3, 7, 9, 10. How will you calculate the standard deviation? What do you have to do first? Nisha? Hidayat Nisha? What do you do to calculate the standard deviation? 1, 3, 7, 9, and 10. What is the first step? Daily students, come on. What is the first step to calculating standard deviation? You have to calculate the mean, right? 1, 3, 7, 9, 10 mean. 1 plus 3, 4 plus 7, 11 plus 9, 20 plus 10, 30, right? 1, 3, 7, 9, 10, 5. So 30 by 5, 6 is the mean. After calculating the mean, what do you do? What do you do after calculating the mean? Harish, what do you do after calculating the mean?
So we take the difference of each element of the mean and square them and
correct. That's all. That's all. And then you take the square root of the whole thing after taking average.
Divided
right?
by the number of people.
Correct. So what do you do? 1, 3, 7, 9, 10. Subtract the mean, which is 6. So that becomes minus 5, minus 3, 1, 3, and 4. Minus 5, minus 3, 1, 3, and 4. Right? So then what you do, use minus 5 square plus minus 3 square plus 1 square plus 3 square plus 4 square. 25 plus 9, 34 plus 1, 35, right? 35 plus 9, 44, and 44 plus 16. So it is 60 divided by the total number of elements, which is 5. So 12. 12 is what? Variance. Square root of the variance is root 12, which is the standard deviation. Do you all understand this? Students, Janani, do you understand this, ma? Janani?
Yes, sir.
Do you understand how to compute standard deviation?
Yes, sir.
Okay. So likewise, let's go back to the bell curve discussion. So there is a statement which is made here, right? What is given? If the RMSE is equal to 50,000, it means 68% of the system's predictions fall within $50,000 of the actual value. What does that mean? Why 68%? So let's come back to the bell curve. So if you have the curve like this, remember, and this is going to be the curve, right? Apologies for the poor drawing. So what's going to be there? This is 2 standard deviations, 1 standard deviation, 1 standard deviation, 2 standard deviations. So how is it divided? So between the first standard deviation, there is 68% of the data. Okay, 68% of the data. So here there is 14% of the data between the first and the second. Likewise, here there is 14% of the data. So 68 plus 28 and 96. Remaining what percent is there? 4% of the data. So that is split equally on both the sides. So here there is 2% of data and here there is 2% of the data points. Correct? This is how a bell curve distribution works, right? So between 1 standard deviation on either side, 68% of the data points are collected. Between the first standard deviation, second standard deviation on either side, 14 plus 14, 28% of the data points are concentrated. Beyond the second standard deviation on either side, 2% each, or 2 plus 2, 4% of the data points are concentrated. Do you understand, everyone? So here what it says is that if RMS is 50,000, that means what is 50,000? Standard deviation is 50,000. Right? That means that 68% of the system's predictions fall within $50,000 of the actual value. Within $50,000, it means plus or minus 50,000. So 68% of the predictions fall within $50,000 of the actual value, and 95% of the predictions fall within 100,000. 2 standard deviations now, it is within 100,000. So it is this one. So we know it is 90. Nammaloda calculation padi evlo varudhu? 96. Right? That's fine, because some people say 13.5. But anyways, we will take for all practical purposes as 34, 14, 2 on either sides. 34 plus 34, 68. 34 plus 14 into 2, right? That will be 34 plus 14, 48 into 2, 96. And then the remaining will be 2% on each side. How many of you understand what I just said right now? And how many of you want me to repeat? How many of you understand? Students, can I please have a show of hands to understand if you've gotten my point? How many of you understand? Yes, no, not really. What are you talking about? I would appreciate some answers. Shubhashweta, do you understand what I'm saying? Shubhashweta? What about Kirtana? Kirtana, you understand? Kirtana, okay, fine. So RMSE, what is the formula for computing RMSE? Let's come to that now. So the formula for computing RMSE is RMSE of x comma h square root of 1 by m sigma I runs from 1 to m h of x minus y the whole square is the same thing, man. It just means the same thing. That is, you're taking the standard deviation of the errors, right? So what do you mean by standard deviation of the error? So predicted value minus actual value will give the error. Supposing I say that the actual value should be 10, but I have predicted as 8. What is the magnitude of error? 2. But if I say the actual value is 10, but I have predicted 12, what is the magnitude of the error? Minus 2. But as far as I am concerned, the magnitude is the only thing I'm bothered with. I'm not bothered about the sign, right? So in that case, what are the only two ways in which the sign can be removed? Either by absolute value or by square. So root mean square value is what is the formula we are looking at. RMSE, 1 by m sigma I runs from 1 to m. M is the number of training instances, right? M is the number of training instances on which you're measuring the RMSE. So for example, if RMSE is validated on 2000 districts, then M equal to 2000, right? And XI, what is XI? It's a feature, it's a vector of all the feature values, right? The vector of all the feature values of the ith instance in the data set, but other than the label, right? For example, in this case, median housing price alone is not there. The rest of the things, population, median income, whatever, all of that forms part of X, right? H of X means by using all these input variables, what is the predicted output? Okay. And Y of I is the actual label, right? So you're going to find out the difference. That's why I say H of X minus Y. Now you're squaring the entire thing because you don't want the sign to affect the value, and you're taking the average and square root of the average. That's why it's called root mean square error. So for example, here we have an example. If the first district in the data set is located at longitude minus 118.29 degree, latitude 33.91 degree, and has 1,416 inhabitants with a median income of $38,372, and the median house value is 156,400, then what do you have as X? Minus 118.29, 33.91, 1416, 38,372. These are the input features of the model. The output is the actual median housing price, which is 156,400, right? That's why they have taken a sample X and Y to show you how do you find out these X and Y values. So X is nothing but capital X. Small x is the individual value. Capital X is a matrix containing all the feature values of all instances in the data set. There is one row per instance, and the ith row is equal to the transpose of Xi. Right? It's a transpose of Xi. So let's look at how this matrix is structured. So X matrix, it is a vertical matrix, whereas capital X is going to be a transpose of all the vertical matrices. So it is going to be minus 118.9, 33.91, 1,416, 38,372. Instead of appearing in the first column, it appears in the first row, right? Because the transpose means switching the row and the column. What is H? H is the system's prediction function. It's called the hypothesis. So when the system is given an instance's feature vector, then it outputs a predicted value, right? That we are calling it y cap of I. We are calling this predicted value y cap of I and the actual value as y of I. So y cap of 1 minus y of 1 is 2000, which means the predicted value and the actual value's difference for the first training instance is 2000. What is RMSE of X comma H? It's the cost function measured on the set of examples using your hypothesis H. So we use lowercase italic for scalar values, right? And function names, and uppercase bold font for matrices. Okay, always as a convention. Uppercase bold font refers to matrices. So generally, RMSE is the preferred performance measure for regression tasks. In some contexts, however, we use some other function. It's called the mean absolute error. Why we use this function is because if you see RMSE has a square to remove the sign. So what happens if the values are becoming further and further from the mean? When you square them, the values will become even larger. Correct? When you square them, the values tend to become even larger. Right? That's the problem. So then what happens here is we will obviously see that the values are becoming very large. So we are going to ensure that we put in the mean absolute error. So mean absolute error ensures there's no squaring. So it removes the squaring with an absolute value. That's the only difference here. Mean absolute error is 1 by m sigma I runs from 1 to m, h of x minus y modulus instead of square. This also removes the negative value. So both RMSE and MAE are used to measure the distance between two vectors, the vector of predictors and the vector of target values, right? So this is something extra. It's just good to remember. Remember that the various norms, right? Norms are basically the different mathematical notations that are used. So MAE is called the L1 norm, right? Whereas RMSE is called the L2 norm, right? Similarly, LKth norm is represented as here. So modulus of V0 power k plus mod B1 power k and so on up to mod Bn power k, the whole power 1 by k. What is happening in RMSE? Substitute k by 2 square root of V0 square plus V1 square plus V2 square, so on up to Bn square, right? So whereas if you look at the zeroth norm, L0th norm, what will happen? Everything power 0. So 1 plus 1 plus 1 plus 1 plus 1, so on, whole power 1 by 1. So what is this going to be? It's going to be the cardinality of the vector. There's a number of elements in the vector. L infinity is going to be the maximum absolute value in the vector, because anything power infinity is infinity. So the higher the norm index, the more it focuses on large values and neglects the smaller ones. Why? For example, let's take a very simple example of squaring. It's a very mathematical concept, right? So for example, if you have the number 6 plus you are adding the number 0.5 to it, right? What is the answer? 6.5, right? What is 0.5 out of 6.5? It is 5 out of 65, which is 1 by 13, correct? 0.5 by 6.5 is 5 out of 65, which is 1 by 13. Now assume you square the value. You square both the values. So what does 6 become? 36. What does 0.5 become? 0.25, correct? It becomes 0.25. Now when you make it 0.25 and when you add it to 36, then what happens? It's 36.25. What is 0.25 by 36.25? 25 by 3625, right? Which is approximately 1 over 100 plus, right? It's more than 1 over 100. So you see that as the values are squared, cubed, and the power keeps on increasing, the larger value dominates, right? The larger value dominates and the smaller value can be ignored, right? How many of you understand this point? As you increase the powers, the larger value dominates and the smaller value can be ignored, right? Likewise here, when you look at L infinity, it's the maximum absolute value. So the higher the norm index, the more it focuses on larger values and neglects the smaller ones. That's why RMSE is more sensitive to outliers than MAE. But when outliers are exponentially rare, right, RMSE performs very well and is generally preferred. If you look at a bell curve shape, outliers are very rare. Why? Because we find that beyond the second standard deviation, we have only 2% of the points on either sides, right? Most of them lie within 2 standard deviations. So there are very few outliers. Is this point clear to everyone? MAE, RMSE, why MAE, why RMSE, what is the L-kth norm, L0 norm, L infinity norm? Is it fine? I'd like to see some messages in the chat. Is it okay to everyone? Come on, guys, don't make me call out your name every time. Is it okay? Yes. Okay. Good. Moving on. So the good practice is to list and verify the assumptions that were made so far, catch issues seriously early on in the process, right? Some district prices that your system outputs are going to be fed into a downstream machine learning system. And we assume that the prices are going to be used as such, right? We are going to assume that the numbers are going to be used, right? However, right, if the downstream system actually converts the prices into categories and just says cheap, medium, or expensive, it's not bothered about the actual price, but whether it falls into the cheap, medium, or expensive category, right? And then uses those categories instead of the prices, then it's not important enough to get the price perfectly right. It's only important that you get the category correct. Okay, so you need not take so much of effort in training your system to improve the accuracy. As long as it falls within the right category, your downstream system can use it for the proper purpose, right? So all your system needs to do is to get the category right. If that is the case, then the problem should have been framed as a classification task and not a regression task. So you don't want to find this out at the last part of the process. So always find out before you design a machine learning system in a pipeline, what is the downstream going to use your data in which form, in what form, what is the purpose, and how it is going to use it. Okay, is that clear, everyone? Moving on. How do you get the data? So here we're going to get the data from the particular GitHub link. One second, I'll just give you the data link. So you've all installed Jupyter Notebook. I hope all of you have installed Jupyter Notebook by now. Everyone, have you installed the Jupyter Notebook, students? Yes, no. Guys, I'm looking for some answers here. Everyone, fantastic. Okay, I'm going to share my Jupyter Notebook. So I want all of you guys to start working on this. Come on, I want everyone to complete the first line, the set of codes here. Can you start typing import OS, import tar file from 6.moves, import URL lib, download underscore root is equal to this link, right? Download. I'm just going to paste this code here in our chat window. Please use it and observe the screen while typing the code. Don't make mistakes. Indentation is important. Okay, I'm pasting it in the chat so that it becomes easier for you to write the code, but don't make mistakes. Okay. I pasted it there. Please copy it, refer to our chat, copy and paste in the Jupyter Notebook and start executing. First part, I want you to execute only the part that I have posted. Once you've done, please give me a yes or done. Okay. Students, I want you to respond with yes once you're done. If you've done this and if you're executing the code and if you're not getting any errors, to run the code, please click on run. Okay. So what are we doing here? We are just taking the path for fetching the data, loading the data set, right? How many of you have done? Only Vaishnavi Devi has said done. What about the rest of you? Yeah, the copy paste பண்ணி align பண்றதுக்கு இவ்வளோ time ஆகும். Come on. Vijay Paul Raj done. What about the others? What about the others? Okay, so let's move on to the next step then. Fetch underscore housing underscore data. Make a call to this function. Fetch underscore housing underscore data. Make a call to this function. Come on. So what happens? It downloads the data and extracts it. It downloads the data and extracts it. Come on. Done. Move on. Now what happens? You are loading the extracted data into a data frame. This is a very important concept, guys. A data frame is, you can think of it as a data type like an array. It's a very critical data manipulation framework that is used. Pandas, it's called Pandas. So import Pandas as PD, def load housing data within the parameters. You provide housing path, and CSV path is os.path.join, give the path and read return pd.read underscore CSV of CSV underscore path. Come on, execute this function. Please look at the screen while writing the function so that you don't have any indentation errors. Okay, only Vaishnavi Devi. What about the others? Come on, students. Are you done? Good. Okay, moving on. Now that we have the data on the pandas, we'll run these two commands. Housing equal to load housing data, housing.head. Head will basically give you the first few elements. First few elements will be visible. How many of you can see this output? Once you execute this, please let me know if you can see the output. Come on, guys. Okay, good, good. So how do you see once you observe the output? You see the the longitude, the latitude, the housing median age, total rooms, total bedrooms, population, households, median income, median housing value, ocean proximity. So we see all these parameters. Now, when you execute the housing.info function, right, it gives you what these parameters are, the data types. So it's used for description of a data set. So when you please execute the housing.info function and let me know if you're able to see a similar output. Execute the housing.info function and let me know if you're able to see a similar output on your screen. Come on, I expect more contribution from guys. Yes, no, good, Sharmila. What about the others? Are able to see a similar output describing what the column is, what is the data type. Good, good. Now, do housing of ocean proximity dot value underscore counts. Now, what is the purpose of this particular function call? Now, what it does is it goes through the column ocean proximity, right? It goes through the column ocean proximity and counts the distinct values that are used to fill the column. Right? Please execute this housing within square brackets ocean underscore proximity dot value underscore counts. Come on. Are you getting this? Can you see less than 1 hour to ocean 9,136, inland 6551, near ocean 2658, near bay 2290, right? And island 5. Yes? Okay, moving on. How do you describe, right, this particular data set? What does the describe function do? The describe function calculates some important statistical parameters. What is the count, the mean, the maximum, the minimum, the 25th percentile, 50th percentile, 75th percentile, right? So please try executing the housing.describe function and let me know if you're able to see all these values for the parameters as it is shown on my screen. Please execute the housing.describe function. Yes, all of you are able to see it. Good. Moving on. Now we are trying to see what is the reason why we are subjecting the data points to all these kinds of inspections is because we are trying to understand the values, right? What are the things we did? We looked at what their data type was through the housing.info, then housing.describe, right? That told us what is the mean median value of all of the parameters, right? So the next thing we are trying to do is we are going to plot the data. We're going to create histograms of the data, right? Using the matplotlib function. Now, come on, I want you to execute this and tell me how the data distributions look like. So these are the data distributions for latitude, longitude, median housing age, total rooms, total bedrooms, and population. Come on, can you do this and tell me if you are able to see the similar thing on your screen? Are you able to see similar data distributions on your screen for all the data parameters? Yes, all of you? What about Vaishnavi Devi? Are you able to see it? Good, good. So, do you see any bell-shaped curves here? Do you see any bell-shaped curves? Any bell-shaped curves? This one is close to a bell shape, right? Okay. Now, before we go further, let's go back a bit to the lesson and understand a few more concepts before we come back, right? So we've done all this and you've seen the histogram. Now, first thing that you notice in the histogram, let's look at a couple of observations here. The median income attribute, it does not look like it is expressed in US dollars, right? Median income. If you look at the median income attribute, right? It does not look like it's expressed in US dollars because obviously $1,600 cannot be the median income, right? So there is some other scale in which it is represented. After checking with the team, you're told that the data has been scaled and capped at 15, right? For higher median incomes and at 0.5 for lower median income. So working with pre-processed attributes is common and it's not necessarily a problem, but you should know how the data was computed. Why? Because if they're going to artificially impose a limit on the data, then what is going to happen? Automatically your training will suffer. Okay? Automatically your training is going to suffer.
Sir, I'm getting error, sir.
What error is there?
Sir, matplotlib model name இல்லைன்னு வருது sir.
Oh, you don't have matplotlib installed, huh?
Sir.
Did you execute all the steps in the median block? There was something for all the library installations also.
Already installed, sir.
Okay. Any error exactly over the screen share panna? One second. I've just enabled screen share. Yeah.
Sir, I'm
No
shared.
module name. Path data. Path data. 1 second. Just hold on.
Sir.
Okay. Can you try a pip install command? Pip install matplotlib kodunga.
Here, sir.
Not here, pa. The command line. Correct. Prompt line.
What, sir?
Pip install. PIP install matplotlib. Wait. Yeah. Pani paranga. Matplotlib.
correct, sir?
Hmm. It's
I
not
think
here.
I didn't download this. It
Papa.
install this, sir.
It's a short package now. Let's see if it is. Okay, finish it and then tell us if it's happening. Yeah.
Sir. Stop, sir.
Okay, so continuing on, students. Yeah, so where were we? Yeah, so what you have to do here is we were talking about the data set, right? How does it look? So we see that the data is capped here. What do you mean by saying the data is capped? You look at the median income, right? The lowest median income is somewhere here. Sorry. Lowest median income is somewhere here, right? Whereas if you look at the highest income, right? The highest income is 15, correct? Lowest income is some 400 something. Highest income is near 15 something, correct? Yes or no? So the data is capped. So you should find out if the data is pre-processed, right? That's what they're saying. Second thing is the median housing. So the housing median age and the median house value are also capped, right? Housing median age and median house value. Let's see. Median house value is obviously capped. Why? Because after this block, there is nothing, right? Before also there's nothing. Okay. And housing median age also likewise after this line, there's nothing. Correct? So they're capped. But what is the problem here? The problem is because your median house value is capped, the machine learning model may think that your prices never go beyond that cap. Because you remember, whatever you train the model with, that is what the model will know, right? It doesn't know anything beyond that. So if you're going to train it in such a way that the data is capped at a certain point, it's going to make the inference that the data cannot go beyond that point. So you need to check with your client team to see if it's a problem. If the predictions go beyond 500,000, then there are two options. One, you can collect proper labels for the districts whose labels were capped, right? Cap panita and the districts ellame they'll take out. So you find out those labels, add them back into the data set, or remove those districts from the training set, right? And also from the test set. And these attributes have very different scales, right? We have to look at something called feature scaling. And many of the histograms are tail heavy. That is, they extend much farther to the right of the median than to the left, right? So this makes it difficult for machine learning algorithms to detect patterns. So we'll be transforming them into bell-shaped distributions. So we see that these population, total bedroom, total room, tail heavy distributions. You see that they have a long tail, right? So it makes it difficult for it to make predictions. So we're going to convert them into bell-shaped distributions. Okay. Before that, we're going to create a test set, right? So we're going to set aside a part of the data voluntarily at this stage, right? But we've just taken a quick glance at the data. Surely you know a lot more about the data before you decide what algorithms to use. But can you tell me why you set aside the data right at this stage? Can anyone here tell me why you set aside data right at this stage? Why do you set aside the data right at this stage? Anyone? Why can't you see the data, scrutinize it, and then set aside for the test set? Is there any problem in that? Come on, guys. Can you answer? Why do you set aside the data before even looking at it? What is the need for that? Anyone? Come on, guys. Why should you set aside data? Very good, Harish. Snooping bias. Snooping bias is the answer. See, when you look into the data, what happens? You detect certain patterns. Your mind stumbles upon certain patterns. And what happens? That influences how you separate the test set later. Right? Obviously, you want your model to perform well. There's an inherent bias. So that's called data snooping bias. So you should never ever peek at the data. You should always set aside the test set before looking at it. So creating a test set is very simple. So you just pick some instances randomly, right? Typically 20% of the data set and set them aside. So that's what we're going to do here. Coming back to our code, let's execute this to pick the test set. Okay, pick the test set. Execute this. I'm going to paste this code in the chat. Right, execute this and then split into the training and the test set. Tell me how many members are there in the training and how many in the test set. Please paste your outputs once you execute this. So you're splitting the data into the training set and the test set.
Sir, answer வந்துருச்சு sir.
Andirtha.
And the mat plot
Good, good. Continue further. Very good. What is the output you got? Devadarshini and Kirtana. How many training? How many tests? Very good. Very good. Okay. So once we have split it into the training and the test set, let's come back. So it's good, but it's not perfect. Why? Because if you run the program again, it will generate a different test set. So over time, what happens? You'll get to see the whole data set, right? Which is something you want to avoid. Why? Because it will lead to overfitting. So one solution is you save the test set on the first run and load it in the subsequent runs. Another option is to set the random number generator seed value before you call the random permutation. So it always generates the same set of shuffled indices. Okay. So, but both the solutions will break the next time you fetch an updated data set. Common solution is to use each identifier to decide whether or not it should go into the test set. So for example, you could compute a hash of each instance's identifier, keep only the last byte of the hash and put the instance in the test set if the value is lower than or equal to 51, right? Why? Because in the instance are down, if you take out the last byte, right, it can only be from 0 to 256. Now, if it's lower than or equal to 51, that's automatically going to be 120, 20% of the values, right? It's only going to be 1/5 of the values automatically, 51 out of 216, right? It's simple probability. This ensures that the test set will be consistent across multiple runs, even if you refresh the data set, and the new test set will contain 20% of the new instances. It will not contain any instance that was previously in the training set. So how do you do an implementation of this? Let's look at the implementation. So let's go to the code again. Students, are you following me? Do you follow what I'm saying? Please give me a yes if you're following. So come on, create this to split the training and test set by index. Come on. Yes, all of you have done it. Okay, good. So let's move on. Right. So once you have separated the test set, the problem is the housing data does not have an identifier column, right? We said that we're going to use the identifier. What is the identifier column? There's no such column. Simplest thing is we can use the row index as the ID, right? That's what we're going to do. So use the row index as the unique identifier, and you're making sure that the new data gets appended to the end of the data set and no row ever gets deleted, right? If this is not possible, then you can try to use the most stable feature to build a unique identifier. You can use the district's latitude, longitude, because they're guaranteed to be stable for millions of years, right? Instead of tectonic movement. So you can use that. Okay. So some of the things that we'll be trying out here is, so we will be trying out creating an index here. Come on, guys. I want you to execute this code as and when I'm showing this and explaining this. Execute it and tell me the output. Likewise, we'll combine the latitude and longitude to create an identifier. Try both of this. If you're done with both, please give me done so that we can move on. What about the others? Good. Now that we are done with this, I want you to understand that there are train test split sets which are already provided by scikit-learn, right? Few functions to split data sets into multiple subsets. The simplest function is the train test split, which does pretty much the same thing as the function split train test, which we defined, with a couple of additional features. First thing is there is a random state parameter that allows you to set the random seed generator, which we saw earlier. And the second is you can pass it multiple data sets with an identical number of rows, and it will split them on the very same indices. Okay, so let's move on and create this piece of code to invoke the train test split method defined by scikit-learn. Come on, please execute this and give me a done so that we can move ahead. Once you're done, just give me a done so that we can move ahead. This is the existing, pre-existing function. Yes, come on, guys. If you've done, please give me a yes. Then by the execute point of the time, come on. Only Diliban. What about the others? Good. Now let's move on. Once we have done that, right? So far we see that we have done only purely random sampling methods. So this is fine if the data set is large enough, right, relative to the number of attributes. But if the data set is not as large as the number of attributes, you risk the run of introducing a significant sampling bias. So for example, when a company decides to call 1,000 people to ask them a few questions, they don't just pick 1,000 people randomly. They ensure that the 1,000 people are representative of the entire population. So for example, if the US population is composed of 51.3% females and 48.7% males, so a well-conducted survey would maintain the same ratio even among the 1,000 people called. So they call 513 females and 487 males. So this is called stratified sampling, right? Population is divided into homogeneous subgroups called strata, and the right number of instances is sampled from each stratum to guarantee that the test set is representative of the overall population. If the purely random sampling method was used, there's only 12% chance of sampling a skewed test set with either 49% male or 54% female. So either way, survey results would be significantly biased. So remember, stratified sampling is used to ensure that the data that you are sampling out is representative of the population, right? It should not, for example, if you're going to have a test set, right, which consists of only one certain kind of data from amongst the data set, then that's not the right representation of the system's performance. It should be exactly mirroring how the data attributes would look in an actual production environment. So that's called stratified sampling. When you divide the data into homogeneous groups called strata, and you sample or take percentage of the right set or amount of data from each of the strata to build the test set, which is representative of the entire population. So suppose you chatted with experts who told you that median income is a very important attribute to predict median housing prices, and you want to ensure that the test set is representative of various categories of income, then what you do is median income is a continuous numerical attribute. It's a number, right? So you need to create an income category, right? You need to create an income category to find out how the value distributions are, because otherwise it's a continuous number, right? You can't just do that. You have to create a category. So let's see, how do you create a category? So this is a histogram of income categories. What has happened here is most median incomes are centered around 2 to 5 tens of thousands of dollars. But some median incomes go beyond 6. So it's important to have a sufficient number of instances in your data set for each stratum. Otherwise, the estimate of the stratum's importance is biased, right? You should ensure the sufficient amount. Romba small strata irundhuduna enna agum, you'll have all strata having equal importance. Romba large strata mattu irundhuduna, they will skew the bias. So there should be sufficient amount of data in each of the strata that you choose. So the following code creates an income category attribute by dividing the median income by 1.5, right? You divide the median income by 1.5, okay, to limit the number of income categories, and round up using ceiling function and merge all categories greater than 5 into category 5. So what is happening here? np.ceiling function, housing of median income by 1.5, right? And housing of income category dot where income category less than 5, then you merge with 5. Sorry, income category is less than 5, then it becomes okay. Otherwise, you merge with 5. Okay. So all incomes that are greater than 5 is merged with 5. Okay. So this is the line that does that. So going back to the code, we execute these two lines. So we split into categories. Why are we doing all this? So in order to perform stratified sampling, we take the most important attribute, which is the median income, right, in order to predict the house prices. So we create income categories called strata, and then we sample from the strata. So that's why we are creating an income category attribute here. Come on, please execute this and give me a yes if you're done. Just execute this, guys. Come on. Okay, good. So now that we've created this housing category, the next step that is there for us is to do the stratified sampling here, right? So stratified sampling is done, and then we're going to check the results of the stratified sampling. So come on, let's do the stratified sampling here and see if you're able to get the right categories. So remember, we're doing the stratified sampling based on the income category, and see if you're able to get a right distribution income. Tell me if you're getting the same results as shown on the screen. If you are, give me a yes. Okay, good. So hope all of you are getting a similar stratified distribution as shown on the screen, right? Okay, the next thing that we're going to do here is you're also going to see, you can measure the income category proportions in the test set, right? You can compare the income category proportions in the overall data set and in the test set generated with stratified sampling. So if you look at this, right, if you look at this, look at the comparison. So in the overall set, you see that the each income category representation parameter, it is some 40%, sorry, some 4%, some 30%, 30%, 16%, 10%. When you go for stratified sampling, you see the representation is 3%, 31%, 35%, 17%, 11%, right? While for the random, right, the error rates are higher. Stratified sampling, it is very close to the actual distribution of strata. And that's why we do stratified sampling. So now once you have sampled, you have to remove the income cat attribute. So that's what we're going to do. So please ensure you execute this code to remove the income category attribute. Okay. Right, you can do this. Drop the income category attribute. But data preparation is extremely important. So we've spent so much time in looking at that. Now, if you take a quick glance at the data to get a general understanding of the kind of data you're manipulating, so we're going to go into a bit more detail and make sure you put the test set aside and you're only exploring the training set. Now, also the training set is very large, so you may want to sample an exploratory set, right, to make manipulations fast and easy. So in our case, the set is quite small, so you can directly work on the full set. So we're going to create a copy first so that we don't modify the original set. So we're creating a copy here inside the variable called housing, strat underscore train underscore set dot copy. So getting a copy inside the variable called housing, and then housing dot plot kind equal to scatter, x equal to longitude, y equal to latitude. We plot and we get this shape. Right, we get this shape. This is the shape of California as well, right? We are plotting the longitude versus latitude. Obviously, it's going to look like a map, right? So it looks like California's map. So come on, plot this and tell me if you're getting the same map. Let me know if you're getting the same map. Give me a yes if you're seeing a similar map on your screen. Good. So then you move on. When you put alpha equals 0.1, right, and you put alpha equals 0.1, what is essentially happening here is that you are highlighting those points which are denser, right, in terms of the values, and those that are weaker are getting in a different shade. Those that are weaker are going into a different shade. Right, alpha equal to 0.1 makes it easier to visualize places where there's a high density of data points. Right, now that's much better. You can see the high density area. So where are the high density? We see Bay Area, Los Angeles, San Diego, plus long line density in the Central Valley. Okay, around Sacramento and Fresno. So most generally our brain is very good at spotting patterns on pictures, but you may need to play around visualization parameters to make the pattern stand out. So we look at the housing prices now. So what we're doing is we're going to create a colored map with the housing prices representing different parts through different colors. So please do this. You'll be able to get a colored plot now. Good. Now we're going to learn about a very important concept here called the correlation value, right? So the image tells you that the housing prices are very much related to the location. And if you see that the prices are becoming higher and higher and higher as you go close to the ocean, the population density, right? So it'll be probably useful to use a clustering algorithm to detect the main clusters and add new features that measure the proximity to the cluster centers. Ocean proximity attribute is also useful, although in Northern California, the housing prices in the coastal districts are not too high. So it's not a simple rule. So how do we look for correlations, right? What is a correlation? So since the data set is not too large, you can easily compute something called the standard correlation coefficient. It's also called Pearson's R value, right? So it is between every pair of attributes and it is done using the CORR method. Right? The correlation underscore matrix is equal to housing.cor. So let us execute this function and understand what is the connection or the mathematical correlation or correspondence between different attributes in the data set. Okay. So please execute the two functions that are sent in the chat. Cor underscore matrix is housing.cor. And once you've done, find out the connection of different variables to the median house value. Come on, execute this and let me know once you've gotten value similar to what you see on my screen. Good. So now that you see these values, 1, 0.68, 0.642274, 0.135097, and you see some negative values. Now, what do these values mean? Right, a correlation matrix or a standard correlation coefficient is equal to a positive value when there is a positive correspondence between attributes. That is, they are directly proportional, crudely speaking. Median housing value is directly proportional to median income. The higher the median income, the higher the value of the real estate in that area, right? The more the number of rooms, the more the value of the property in the area. The more the median age, the more the value of the property in the area. That's why all of these have positive correlation coefficients. Why does median house value have 1 as a correlation coefficient? Because it is the same term, right? Whereas if you look at population, latitude, longitude, they have negative correlation coefficients. That means they're inversely related to each other. The higher the population, the lower the price. Obviously, because more people are there, the area is obviously going to be less expensive, so lower the price. It's very dense, right? Likewise for longitude and latitude. So please keep in mind that the correlation coefficient ranges from -1 to +1. When it's close to 1, it means there's a strong positive correlation. The median house value tends to go up when the median income goes up. When the coefficient is close to -1, it means that there's a strong negative correlation. You can see small negative correlations between latitude and median house value, right? Finally, coefficients close to 0 means there is no linear correlation. Please remember this. When the median is close to 0, it means there is no linear correlation. It doesn't mean there is no correlation. It just means there is no linear correlation. And you can see various plots along with the correlation coefficient between their horizontal and vertical axis as shown. Right? If you look at the 0 value, so 1 pathingana, it looks like a straight line. -1 pathingana is a downward sloping line. +1 is an upward sloping line for the correlation coefficient. If you see 0, it can be in any of these forms. It just means that the relationship between the parameters are non-linear. Right? There's no linear correlation. It can be that there is some other kind of correlation also. So correlation coefficient measures only linear correlations. It may miss out completely on non-linear relationships. Right? Note that how plots of all the bottom row have a correlation coefficient equal to 0, despite the fact that their axes are clearly dependent on each other. Right? So these are examples of non-linear relationship. The second row shows examples of correlation coefficient equal to 1 or -1. Right? This is nothing to do with the slope. And another way to check for correlation between attributes is to use the Pandas scatter matrix function. It plots every numerical value against every other numerical attribute. Since there are 11 numerical attributes, you'll get 121 plots. It will not fit on a page. So we'll just look at certain promising attributes to compute the values. So we're going to compute every attribute against every other attribute, right? That's what we're going to do here. Please execute this function inside this code. And let me know if you're able to see a graph of this nature. If you have been able to see these graphs, please give me a yes, so we can move on. So this shows every attribute plotted against every other attribute. Okay, good. So you're able to see all these plots. In this plot, you can clearly observe that some of the attributes show an upward trend. Which are the ones? You see median income versus median housing value. Though it looks a bit scattered, it shows an upward trend, right? Likewise, if you see median housing value versus median income, same thing, shows an upward trend, right? So that's what we are trying to observe from this, okay? So the main diagonal would be full of straight lines if Pandas plotted each variable against itself. So instead of displaying that, it displays a histogram of each attribute. So obviously a variable against itself is going to be only one. So the only promising attribute here to predict median housing value is the median income. So if we zoom in on the scatter plot, we'll be able to see something of this nature, right? So the plot reveals a few things. First thing is there is a correlation which is very strong and powerful. You can clearly see an upward trend and the points are not too dispersed. Secondly, the price cap we noticed earlier is clearly visible as a horizontal line, right? Remember the price cap we were talking about, there's no price beyond 500,000, right? And likewise, there is one other, obvious but less obvious straight line, a horizontal line around 450,000. You can see one here and one around 350,000, right? You also see one around 280,000. So there are some kinds of lines that you observe here and there as well, right? You may want to try removing the corresponding districts to prevent your algorithms from reproducing these data quirks, right? So experimenting with attribute combinations. So hopefully the previous sections we saw, it gives us a few ways of how you can explore the data and gain insights. You can identify a few data quirks that you want to clean up before feeding the data to a machine learning algorithm. And you found interesting correlations between attributes. So with the target attribute also, and you notice that some attributes have tail heavy distribution. So you may want to transform them by computing the algorithm or something. And of course, your mileage will considerably vary with each project, but the general ideas that you use are similar. One last thing which you want to do before you actually prepare the data for machine learning is to try out various combinations, right? Total number of rooms in a district is not very useful if you don't know how many households are there. So you don't really want the total number of rooms per district. You want them per household. So total number of bedrooms by itself is not very useful. You probably want to compare it to the number of rooms, right? And the population per household also seems like an interesting attribute to look at. So we are transforming certain attributes, right? We are transforming certain attributes from what they are to a different value. That's what we're doing here. Please execute this and then compute the new correlation matrix values. Please execute this code and compute the new correlation matrix values. Once you've done, please tell me. Once you're done with this, please let me know. Good. So what are the new correlation matrix values? We observe that once we computed the new attributes, you see bedrooms per room, right? Likewise, the other one we computed was rooms per household, right? We see that they have stronger correlation matrix values, right? We see they have stronger or higher correlation matrix values. So one thing we can understand is obviously that means these new attributes are more meaningful. So we at times are constructing new attributes in order to have stronger and more meaningful relationships. So the new bedrooms per room attribute is much more correlated with median house than the total number of rooms or bedrooms. Apparently, houses with lower bedroom per room ratio tend to be more expensive, and the number of rooms per household is also more informative than the total number of rooms in a district, obviously, because the larger number of rooms, the larger the house, the more expensive they are. Now, this round of exploration does not have to be absolutely thorough. The point is to start off on the right foot and quickly gain some insights that will help you get a reasonably good prototype. So as you can clearly see in this example, we were able to make some intelligent guesses. However, it may not be that easy for every domain or every data set that you're operating in. And this may be an iterative process. And once you get a prototype up and running, you can analyze its output to gain more insights and come back to the exploration steps. So preparing the data for machine learning, you should write some functions to prepare the data for machine learning, right? So that it can allow you to reproduce the transformations on any data set. We gradually build a library of transformation functions that can reuse in future projects. And you can use these functions in your live system to transform the new data before feeding it to your algorithm. So this will make it possible for you to easily try various transformations and see which combinations of transformations works best. Right. So first, let's revert to a clean training set and separate the predictors and labels. Right. Whenever we create a machine learning algorithm, we have to first separate the predictors and the labels because we don't necessarily want to apply the same transformation to the predictors and to the target value. So let's start off with that as the first step, separating the predictor and the label. Come on, please execute this. Once you're done, please let me know. Once you're done with this, please let me know, students. Good. Good. So before we look into the next part, one thing we need to understand is most machine learning algorithms cannot work with missing features, right? So we need to create a few functions to take care of missing features. Total bedrooms attribute has some missing values, right? In our data set. So we have three options. We can get rid of the districts which don't have the bedroom values, or you can get rid of the whole bedroom attribute itself because it's missing some values in some cases, or you can set the values to some value, right? Missing parameters to some value, either 0 or the mean or the median, right? You can do any of these three functions using the data frames predefined functions called drop NA, drop, and fill NA, right? So drop NA means drop the attribute, drop would drop the particular attribute completely, and when you fill it with the median, it's fill NA, okay? So if you choose the third option, right, which is to compute the median value on the training set and use it to fill the missing values, then also don't forget to save the median value that you have computed, right? You will later need it to replace missing values in the test set when you want to evaluate the system, right? Also, when the system goes live, to replace missing values in the new data. So scikit-learn basically provides a handy class to take care of the missing values. So it's called the imputer class. So please remember, it's a very important concept. The imputer is basically used to handle missing values in a data set, right? You need to create an imputer instance and specify that you want to replace each attribute's missing values with the median value of that attribute. So how do you do that? Let's look at how do you handle the imputer. So this is how you do it. You declare an imputer and you tell it that you would like to replace each value with the median. So you say strategy is equal to median. Strategy is equal to median. And then what do you do? Obviously, because ocean proximity is not a numerical attribute, you drop ocean proximity from the data. Housing underscore num equal to housing dot drop of ocean proximity comma axis equal to 1. So you drop the entire column ocean proximity, and then you do an imputer dot fit, right? Then you do an imputer dot fit housing underscore num. Right? You do an imputer dot fit housing underscore num. The imputer has basically computed the median for each attribute and stored the results in the statistics underscore variable. So only the total bedrooms attribute had missing values, but we cannot be sure that there won't be any missing values in the new data for other attributes once the system goes live. So it's safe to apply the imputer to all the numerical attributes. So if you do imputer dot statistics underscore function, right? If you do the imputer dot statistics underscore function, come on guys, try it out. Imputer dot statistics underscore. Then you're going to get all the computed values, the computed averages. Once you're done with that, please give me a yes. If you've gotten the values of imputer dot statistics underscore as shown on my screen, please give me a yes, guys. Okay. Once you're done with that, right? Once you're done with that, you can also check the housing underscore num dot median values, right? That will also yield the same answer, right? So I'm also going to get you the same answer. Now you can use this trained imputer to perform or transform the training set by replacing the missing value by the learned median. So what do you do? Imputer dot transform of housing underscore num. Right? So let's execute this to transform the training set appropriately by replacing the missing values with the medians. X equal to imputer dot transform of housing underscore num. So we're going to get a plain NumPy array containing the transform features. If you want to put it back into the Pandas data frame, right, all you have to do is you have to convert it back into a Panda data frame and put it in the housing underscore tr equal to pd dot data frame of x comma columns equal to housing underscore num dot columns. So now you have the Pandas data frame with the data remedy. Now, scikit-learn's interface is very consistent, right? So there are three different types of interfaces. Estimators are basically an object. Any object that can estimate some parameters based on a data set is called an estimator. An imputer is an estimator because it estimates the median. Estimation itself is performed by the fit method, right? It only takes a data set as a parameter or two for supervised algorithms. The second data set contains the labels. Any other parameter needed to guide the estimation process is considered a hyperparameter, like the imputer strategy. And it must be set as an instance variable, right? Generally via the constructor. Then we have the transformers. Some estimators can also transform a data set. Imputer can also transform the data set. The API is again very simple. Transformation is performed by the transform method with the data set to transform as a parameter. It returns the transformed data set, and this transformation generally relies on the learned parameters, as is the case for an imputer. So all transformers also have a convenience method called fit_transform that's equivalent to calling the fit and then the transform, right? The third one is the predictor. Some estimators are capable of making predictions given a data set. They're called predictors. Linear regression model, the previous topic, is a predictor. It predicted life satisfaction given a country's GDP. So a predictor has the predict method that takes a data set of new instances and returns a data set of corresponding predictions. It also has a score method that measures the quality of the predictions given a test set. Okay. Right. So we had estimators, transformers, predictors. Okay. So inspection, all the estimators, hyperparameters are accessible via public instance variables, imputer.strategy, and all the estimators learned parameters are accessible via public instance variables with an underscore suffix, like imputer.statistics_. Datasets are represented as NumPy arrays or SciPy sparse matrices instead of homemade classes. Composition, existing building blocks are reused as much as possible. It's possible to create a pipeline estimator from an arbitrary sequence of transformers by a final estimator. So we're going to see it's possible to create a composition of all these transformations. Okay? There's a sensible default for most parameters. Now, handling text and categorical attributes. So earlier we left out the categorical attribute ocean_proximity. Why? Because it's a text attribute, so we cannot compute the median. But most machine learning algorithms prefer to work with numbers. So let's convert the text labels to numbers. So it's called label encoding, right? Let's do the label encoding to convert the ocean proximity from text to numbers. Please execute the code and let me know if you've done. Guys, are you done? Come on, give me a done once you're over. Waiting for you guys to complete it. Good. Good. So what happens here essentially? It converts. So this is better. So we can use the numerical array in any ML algorithm. So you can look at the mapping that the encoder has learned using the classes attribute. So if you do print encoder classes underscore, you'll be able to see what is the mapping, right? You can see less than 1 hour ocean is 0, island is 1, right? So on and so forth. Now, one issue with the representation is that ML algorithms will assume that two nearby values are more similar than two distant values. That's a problem because by nature, 0 and 1 are closer than 0 and 5, right? But while doing a text to number mapping, that may not necessarily be the case. right? Obviously, you see 0 and 4 are more similar than 0 and 1. Less than 1 or 2 ocean and near ocean are very similar, but less than 1 or 2 ocean and inland are totally different. But category wise, they are 0 and 1, and this is 0 and 4, correct? So to fix the issue, a common solution that you do is to create one binary attribute per category, right? One attribute equal to 1 when the category is less than 1 or ocean, and 0 otherwise. Another attribute equal to 1 when the category is inland, and 0 otherwise. This is called one hot encoding, right? Because only one attribute will be equal to 1 while the other will be equal to 0. So one hot encoding, right? So scikit-learn provides something called the one hot encoder to convert integer categorical values into one hot vectors. Right? Let's see how to do that. So you'll get a one hot vector here. So you see only one of the values are 1, the rest all are 0. Clearly tells us which value has been highlighted here. Right? So there is no issue of the machine learning algorithm making any inferences because there's no 1, 2, 3, 4 here. The 1 is there at some position, right? So here there can be no inference of closeness. That's why we're using one hot algorithm. Please remember this case. Reason for using one hot algorithm is because we don't want the machine learning algorithm to make any assumptions about how close one attribute is to the other, right? So the output is a SciPy sparse matrix, right? It's not an NumPy array. It's very useful when you have categorical attributes with thousands of categories. After one hot encoding, we get matrix with thousands of columns full of zeros, but only one column is going to be 1. So you're using tons of memory, mostly to store zeros, which is very wasteful. So it's called a sparse matrix where only the location of the non-zero elements alone are stored. It's like a normal 2D array, but if you want to convert it into a dense NumPy array, all you have to do is you convert it to using the 2-array function, right? So sparse matrix means only the non-zero elements are stored, but if you want to convert it into a dense array, you can just make this call, right? Is that clear, everyone? So moving on. So we can apply both transformations, that is from text to integer and then integer to one hot vector in one shot using something called the label binarizer class. So text to integer, integer to one hot vector can directly be done using the label binarizer class. So please execute this, the label binarizer. Please execute the label binarizer class. So this returns a dense NumPy array by default. Once you're done, please tell me. Once you're done executing the label binarizer class, please let me know. Done? Good. Now, we already saw how the transformers work, but although scikit-learn provides many useful transformers, you may need to write your custom cleanup operations or combining specific attributes like we saw. So you want your transformer to work seamlessly with scikit-learn functions like pipelines, and since scikit-learn relies on duck typing, right, not inheritance, all you need to do is to create a class and implement 3 methods called fit, transform, and fit underscore transform. We already saw that, right? They have a consistent interface. You can get the last one for free by simply adding the transformer mixin as a base class. If you add base estimator as a base class, then avoid args and k-args in your constructor. You get 2 extra methods, which is get params and set params. That will be useful for automatic hyperparameter tuning. So let's see a simple transformer class for the transformations that we discussed for our data set. Please observe. Let's go through the class to understand what it does. So what it does here primarily is that it has an init function. Obviously, it initializes the bedroom per room. There's the fit function, which basically doesn't do anything. There's a transform function where the rooms per household is computed as the total number of rooms divided by total number of households. Population per household is computed as total population by total number of households. If self dot add bedrooms per room, and what do? You compute the bedrooms per room by x of bedrooms underscore ix by x of rooms underscore x. Basically, you compute the total number of bedrooms per room and you return these three attributes. Else, you just return the two attributes. Okay, so this is called the combined attributes adder, which is a custom transformer written by you. So it computes three attributes: rooms per household, population per household, and bedrooms per room. Okay, is that clear, guys? These are the three attributes that are computed by this custom transformer class. You are writing the transform. Here we don't want the bedrooms per room, right? So we are going to set that value to false. That's why you're setting add bedrooms per room as false. So it is not going to go for that loop. It's just going to return two values, which is rooms per household and population per household. Then finally, you call the transform function. How many of you are done with this? If you're done, please give me a yes. So this in this example, basically the transformer has one hyperparameter, which is add bedrooms per room, which is set to true by default. So this hyperparameter generally allows you to easily find out whether adding this attribute helps the machine learning process or not. More generally, you can add a hyperparameter to get any data preparation step that you're not 100% sure about. So the more you automate the data preparation steps, the more combinations you can automatically try out, making it more likely to find a great combination. So basically, you're trying to check if these parameters are going to give you the needed value add or not. So by setting them as true and false and observing the comparative performances, we can decide if this parameter is a useful one to go with or not. Please give me a yes if you're done. Only Diliban, what about the others? Good. So one of the important transformations that you have to apply is called feature scaling. Guys, we'll go up till 5:30, so 10 more minutes. So feature scaling. So with few exceptions, machine learning algorithms don't perform well when the numerical attributes have different scales, right? We already saw the case for the housing data. Number of rooms range goes from 6 to 39,320, while in medium income ranges from 0 to 15. Basically, they are not in the same scale. So there are two ways to get all attributes to the same scale. One is called min-max scaling. The second way is called standardization, right? Min-max scaling is what people call normalization. Values are shifted and rescaled so that they end up ranging from 0 to 1, right? So what do we do in this? We just subtract the minimum value and divide by maximum minus minimum. Scikit-learn provides a transformer called min-max scaler, which automatically does this. It has a feature range hyperparameter that lets you change the range if you don't want 0 to 1, right? Standardization is quite different. It first subtracts the mean value and then divides by the variance so that the resulting distribution has unit variance. And unlike min-max scaling, standardization does not bound values to a specific range, which may be a problem for some algorithms. However, standardization is much less affected by outliers. Suppose a district had a median income equal to 100, right? So the min-max scaling would then crush all values from 0 to 15 to 0 to 0.15. Why? Because it's the value minus minimum by maximum minus minimum. So if maximum is very high, obviously the values are going to get crushed to a smaller range. Whereas standardization will not be affected. Standardization will just subtract the mean, divide by the variance, x minus mu by sigma, right? So standardization, if you look at it, the standard scaler is provided as a transformer by scikit-learn. So as with all transformations, it's important to fit the scalars to the training data only, not to the full data set, right, including the test set. Only then can you use them to transform the training set and the test set. Okay. Transformation pipelines. There are many data transformation steps that need to be executed in the right order, but fortunately, scikit-learn provides the pipeline class to help with sequences of transformations, right? So if you have 2-3 transformations one after the other, the pipeline can help you execute them in sequence, right? So let's look at this pipeline. See this pipeline, there is an imputer, right, with the median strategy. There's the attribute adder, which we saw, right? And there is going to be a scalar. There are three transformations that you apply, right? Please execute this code in your Jupyter notebooks. We're creating a pipeline which applies three transformations. Right? Three transformations are applied. So here, guys, if you notice, a lot of focus is on preparation of the data. Right? So the pipeline constructor takes a list of name or estimator pairs as a sequence of steps. All but the last estimator must be transformers, right? They should have a fit underscore transform. Last one is a scalar. So when you call the pipeline's fit method, it calls the fit transform sequentially on all transformers, passing the output of each call as the parameter to the next call until it reaches the final estimator, for which it calls the fit method. So pipeline exposes the same methods as the final estimator. The example, the standard scalar, which is a transformer. So the pipeline has a transform method and applies all transforms to the data in sequence, right? So you have a pipeline for numerical values. You also need to apply the label binarizer on categorical values. How do you join the two transformations into a single pipeline? So it has something called a feature union class. So remember, we have two different transformations. One is for numerical, one is for categorical. So you have a feature union class to combine the two pipelines. You give it a list of transformers, right? And when its transform method is called, it runs each transformer's transform method in parallel, waits for the output, concatenates them, and returns the result. So a full pipeline handling both numerical and categorical attributes may look like this. So guys, are you done with the numerical attribute pipeline? So I'll just give you the entire one with the numerical and the categorical attributes. Please look at this one. And I'll explain this in detail. There seems to be some issue in pasting it. Maybe see if you're able to type it out by looking at my screen. Share the screen of that part. See if you're able to type this out. I don't know what's the problem. Oh. So data frame selector, we have the base estimator and the transformer, right? And then we have the label binarizer. And then what are we doing here? We're combining both these attributes. Is it not right? Select. Okay, guys, I guess we'll stop it till here. I don't know what's the reason why it's not allowing me to paste the code. We'll continue with this in the next class. Okay. Thank you. Thank you, everyone. Are all your doubts cleared till now? Any questions for what we did today? Any doubts? Were you all able to follow what I was doing? Students, any doubts, any questions? All good? All good so far? Only Dileepan has any doubt or question or he's the only one who's clear. What about the rest of you? All good? Okay, so let's meet next class and we'll continue this. Okay, thank you everyone. The video for this class will be made available. You'll get the link and you'll be